You ever wonder what kind of force can build mountains so tall they literally scrape the sky? Or what makes the ground suddenly shake in a place like California? Well, the answer to both is actually the same thing, and it's happening right now, deep beneath our feet, in a kind of slow-motion dance that shapes our entire planet. All right, let's get into it.
In this explainer, we are going to get to the bottom of Earth's restless surface by taking a close look at what we call plate boundaries. Think of these as the action zones, the places where all the geological drama happens that shapes the world we know.
So, first things first, what are we even talking about here? Earth's hard outer shell, the lithosphere, it isn't one solid piece. Nope. It's actually shattered into these huge interlocking puzzle pieces called tectonic plates. The best way to picture it? It's kind of like the cracked shell of a hard-boiled egg.
Now, how in the world can a chunk of rock the size of a continent actually move? Well, it turns out these massive plates are floating on a much hotter, softer, almost taffy-like layer of the mantle. It's called the asthenosphere. And because it's so pliable, it allows the rigid plates on top to drift, to collide, and to slide past each other over millions of years.
All that movement brings us to our first type of interaction. Let's kick things off with what happens when two plates decide they need some space. We call this the Great Divide, or more scientifically, a divergent boundary. The name really says it all, you know? At a divergent boundary, two plates are pulling apart, moving away from one another. It's this super slow motion separation that creates a huge gap in the Earth's crust.
So you might be asking, what fills in that gap? That's where things get really interesting. As the plates pull apart, hot molten magma from the mantle oozes up to the surface. It then cools down, hardens, and voila, brand new crust is formed. This is literally how our planet makes new ground for itself.
And if you want a perfect real-world example, look no further than the Mid-Atlantic Ridge. It's this gigantic mountain range running right down the middle of the Atlantic Ocean, completely underwater. It's a massive divergent boundary where new ocean floor is being made constantly, pushing continents like North America and Europe farther apart. We're only talking a few inches a year, but get this, it's so powerful that the undersea communication cables connecting our continents have to be laid with extra slack just to account for this constant stretching.
Okay, so if plates are moving apart in some places, they have to be coming together somewhere else, right? Exactly. And that brings us to our next type of boundary, which is all about a head-on collision. It's time for the big crunch, convergent boundaries. This is the polar opposite of what we just saw. At convergent boundaries, two plates are on a direct collision course, moving straight toward each other. And believe me, when two continent-sized masses slam into one another, the results are, well, they're pretty spectacular. What happens next depends entirely on what is doing the colliding. You can see it here in the table. If a dense oceanic plate crashes into a lighter continental plate, the heavier ocean plate gets forced underneath. That's a process called subduction, and it creates volcanic mountains like the Andes. But if two continents collide, neither one wants to give way, so they just buckle and crumple upwards, creating absolutely colossal mountain ranges like the Himalayas. And if two ocean plates meet, one subducts under the other, forming volcanic island chains, just like the islands of Japan.
So, the bottom line is, all of this grinding, sinking, and crumpling generates an unbelievable amount of stress in the Earth's crust. And when all that stored up energy is finally released, you get some of the most powerful earthquakes and volcanic eruptions on the entire planet.
Okay, so we've had plates pulling apart and plates crashing together. But there's one more way they can interact. It's more of a sideways slip, and it happens at what we call transform boundaries. At a transform boundary, there's no new crust being made and no old crust is being destroyed. Instead, you've got two plates grinding past each other horizontally, in opposite directions. It's like two cars scraping past each other on a highway, but on a planetary scale.
The real problem here is that the edges of these plates aren't smooth at all. They're jagged, so they get snagged and stuck on each other because of all the friction. But the rest of the plates keep trying to move, so this incredible pressure starts to build up right at that sticking point, and eventually that pressure becomes too much, and the rocks snap, causing the plates to suddenly lurch forward.
And that sudden, violent slip, well, that's an earthquake. And the most famous example on Earth is the San Andreas Fault in California. That fault line is the boundary between the Pacific Plate and the North American Plate. And all that sideways slipping is exactly why the region gets so many earthquakes.
All right, so we've seen plates diverge, converge, and transform. But what's the big takeaway here? Let's zoom out for a second and look at why this whole process is so fundamental to the world we live in. Let's just break it down one last time. Divergent boundaries. Plates move apart, new crust is made. Convergent boundaries.
Plates move together, crust is either destroyed or pushed up into mountains, and transform boundaries. Plates slide past each other, releasing massive amounts of energy as earthquakes. Just 3 basic motions, but with truly planet-altering results. And look, this isn't just some abstract science lesson. Understanding these boundaries is absolutely critical. It allows scientists to pinpoint areas that are at high risk for earthquakes and volcanoes. It helps us understand how precious resources and mineral deposits are formed, and it even lets us trace how our continents have drifted across the globe for hundreds of millions of years. Ultimately, it all comes down to this really powerful idea. The ground beneath our feet feels totally solid and permanent, right? But in reality, it's in a constant state of slow, powerful change. Our planet is, in a very real sense, a living, breathing geologic machine. So I'll leave you with a final question to think about. Since we know these plates are never going to stop moving, what do you think our planet will look like millions of years from now? What new oceans might open up? What new mountain ranges might rise to touch the clouds? The forces that we've talked about today, they're busy drawing that new map right now.